Hey everyone, welcome back to the channel. I hope you guys are doing pretty well. So we will see today's daily challenge on Leetcode and let's try to solve it together. So we have this find kth bit in the nth binary string problem. Given two positive integers n and k, the binary string Sn is formed as follows. Uh, S1 is always 0, and then for I greater than 1, S of I is calculated as S of I minus 1 plus 1 plus you reverse and invert the S minus 1 string. Okay, reverse and invert it. Okay, so if you see the example, in reverse means just string is reversed, invert means all the bits in the string is inverted. Okay, if you see the first four strings, S1 is 0, it is already mentioned as the base case. S2 is nothing but you add a 1 after the previous one. So you take the previous string, okay, you add a 1 and then you reverse and invert this previous string. You will better understand it in S3. If you see S3, you have S2 is this 0, 1, 1. Then you add a 1 to it in the middle and then you reverse and invert it. So if you reverse this 0 1 1, it will be 1 1 0, and if you invert it also, it will be 0 0 1. Okay, so you append this 0 0 1 into your S3 to get your final S3. Okay, so if you try to see S4, how do we get S4? First we write S3, then we write a 1, and then we reverse and invert it. So if you do not know how reverse and inverted means, so see, this 1 is going to 0, this 0 is going to 1, this 0 is going to 1, then this triple 1 is going to a triple 0, and then this 0 is going to a 1, last one. First 0 is going to a last one. Okay, so that's how the string is constructed, S1 and all the strings. Okay, and now you need to return the kth bit in Sn. It is guaranteed that k is valid for the given n. Okay, so you see you have n equals to 3 and k equals to 1. So for n equals to 3, S3 is nothing but this, and k equals to 1 means the first bit only you need to return, which is nothing but 0. Okay, and for n equals to 4, k equals to 11, if you see, you need to return the 11th bit in S4. So in this S4 you simply return this 11th bit, okay, which is nothing but 1. So you simply return 1. So that's all about the understanding. I hope the question is at least very clear to you, and there is no doubt in the question at least, and you should definitely try this problem on your own before continuing to watch this solution. Okay, so yeah, let's start. Uh, so first we will write some strings and we'll try to simulate, and we will try to develop some intuition of what is the pattern behind this. Okay, what pattern we can see and how much can we actually optimize it. So we have this S0, S1, not S0, we have S1, right? Which is nothing but a simple zero string. We have S2, we can calculate how. Reverse and invert this string. So if you reverse this string, you get 0, you invert this string, you get 1. Okay, and you append this 1 after appending a 1. So after this S1, you append a 1 by default, and then you append this 1. That's how you get S2. I hope it is understandable. And we will continue with writing the future elements S3. So you write S2 at first, then you add a 1, then you invert and reverse it. So, or reverse and invert it, whatever, the answer will be the same. So if you reverse it, you get 1 1 0. If you invert it, you get 0 0 1. So 0 0 1. Okay, and that's how it is calculated. And if you calculate S4, uh, I am writing the answer directly. After writing this S3, you write a 1 and then you just copy this and invert this. Okay, you can write it in this way also, triple 0 and then 1. So yeah, I hope at least the question is clear. And yeah, these are the first questions. Now can you see some pattern? Can you try to see some pattern or any basic kind of observations can you see and note it down? Okay, so yeah, first thing is that you will be given an n and k, right? So in Sn you need to find the kth string. Now, the thing is, if you, let's say n is very large, then Sn will also be very large, okay? But if you are asked to find a small k, so let's say if you are asked to find this third in S4, you are asked to find k equals to 3, this third bit, okay? Now, this third bit is 1 in S4 also, in S3 also, in S2 also. So why will you generate this whole string? So I am talking about the case where let's say n equals to 4 and k equals to 3. Okay. Now this third string is 1 in S2, S3 and S4 also. So why will you generate this large string and waste your time? Okay. So if you are thinking of a brute force manner, I will try to tell you to optimize it. Okay. Because you do not need to generate this whole n. So essentially you can say that generating this n is useless. This n in the question is useless. Only this k is sufficient. If you ask me that, hey, for k equals to 3 you find out, then I should automatically be able to tell you that k equals to 3 is present in which minimum Sn. Okay, which minimum Sn this k equals to 3 is present. So you can tell that, hey, every time the string is something like the length of the string is becoming into 2 plus 1, again into 2 plus 1. So if you try to observe any pattern for s of I, so if it is s of I, the pattern is nothing but 2 to the power of I plus 1 minus 1. If you see 2 to the power I plus 1 minus 1, how I'm getting this? For 2, you put S2, for S2, you put I equals to 2, you get 2 to the power, uh, no, not 2 to the power I plus 1 minus 1, sorry. This is simply 2 to the power of I minus 1. Because for I, if you just put I equals to 2, it's 2 to the power 2, it's 4, minus 1, it's 3. So length is 3. So length of this string is nothing but s of I dot length is nothing but 2 to the power of I minus 1. So it is nothing like you can just find the log. Okay, find the log of k plus 1. This is the value which is the minimum n. Okay, the minimum n where this k is present. Okay, you can calculate it this way, or you can do some other methods also. So basically my point is that you do not need n at all. You can easily find n. Okay, find the minimum n where k is present. So yeah, for if you are asked n equals to 4 and k equals to 3, you will never go to n equals to 4. You in n equals to 2 only, you will just simply return that, hey, here I am getting my k and this will be my answer. So this is one observation. Okay, now the second and the main idea which should come to your mind is that, let's say you are asked to find a particular string, a particular length. So let's say I will tell that, let's find for k equals to 11. Okay. Now, if you try to see which is the 11th bit over here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you see the 11th bit is this. Okay. Now you see how is this 11th bit derived? This is the middle bit, okay? This is the middle bit. So you reflect this 11 bit, you see. So how if you reflect it, you can say that this is derived from this 0, okay? This was 0, so you just inverted it. You just inverted it. That is flip the bit, okay? Now this 0, again, this is the middle index here. Now this 0 is derived from this one, okay? Now this particular one is derived from this 0, and this 0 is nothing but the s10, which is the base case. Okay, this is the base case. Okay, so every number in this string, so I calculated for n equals to 11. Okay, let's see for, let's say, another number, n equals to 12. I hope you do understand how I'm tracking. Let's calculate for n equals to 12. This is the 12 bit. Okay, this is our 12 bit. Now this was our middle bit. So uh, what is the reflected index for this? The reflected index is this, which is derived from this. Okay, now you see this is the middle element, and you can easily understand the middle element is always 1. Middle element is always 1, because that is the definition of the problem, right? At the middle you append a 1 and then you reverse and invert the string. Okay, so this also you can get recursively. So if you try to iterate recursively, so we talked about n equals to 11, n equals to 12. Let's talk of one last case, n equals to 13. Okay, so let's see for n equals to 13 how we will track this. So this is our 13th bit, and we can see that this is reflected from this bit, and this is nothing but this derived from this bit. Okay, and this bit is in the first half of S3. So yeah, it is essentially nothing but S2 only, and this S2 is derived from this bit. This bit is derived from this S1 only. Okay, so I hope you do understand that no matter what bit you give. So see, I talked about F's N11, N12, N13. Not N, K, okay? Kth bit. You need to find the kth bit. So uh, no matter which bit, my next observation is that no matter which bit you are asked, okay, it can always be recursively mapped. It can always be recursively mapped to to either base case equals to 0. So you see that for k equals to 11, you were able to map it to the base case 1 and base case 0. And also for this k equals to 13, both of these numbers, you were able to map it to the s equals to 1, base case 0. So you just say that, hey, this 0 is derived from this one is derived from this 0, and so on. You go on like that. So that is what, no matter which bit you are asked, you can always, it can always be recursively mapped to either base case 0 or middle element 1. Okay, middle element 1. So that is how you see in k equals to 12, when you took k equals to 12, you saw that this was derived from this this one, and this one is nothing but the middle element of the previous number. So this is also recursively derived from the middle element. Okay, and these two are derived from the first index from the base case S1, which is nothing but 0. Okay, which this can be traced back to S0, the base case. Okay, so I hope you do understand that everything is derived from either the middle element or the first element. So you can write a recursive function for this very easily, and it should not be any problem. I hope the approach is at least very clear, and as we will write the solution, it will be more simpler. And yeah, now one thing is that as we do not require n for this, we require the minimum n in which k is seen. So yeah, at every time you see, if you get k equals to 11, then when n can be 1, right? When then n is 1, uh, so for 1 you cannot obviously get k11. So for n equals to 2, you can see that it is nothing but 2 square minus 1, which is nothing but 3. Now 3 obviously also you cannot get. Now for n equals to 3 also you get something like this, 7. Length of the string is 7. Again you cannot get. N equals to 4, 2 power 4 minus 1, so 15. This 15 length string for n equals to 4 only is the minimum one. Okay, and how will you derive this minimum n from k? Again, you can do this log of k plus 1, or you can just count the number of bits in k. This is same thing, right? So this 11 can be written in binary is this, and if you count the number of bits, it is 4. So that is nothing but the value of n. Okay, so in this way also you can find the number of bits in this k. So first of all, I can easily write the base case. So if we have this k equals to 0, right? Or k starts from 1, right? It is a 1 based indexing. Yeah. So if k is 1, you simply return a 0 because this is our base case, okay? And now you try to find the size, okay? Find the minimum n or the size. So int size is nothing but, as I say, radio, the minimum n, it is the number of bits in k. Now the number of bits in k can easily be calculated by this function 32 minus built-in CLZ of k. What does this function do? Built-in CLZ, it gives you the number of leading zeros, and 32 minus that is nothing but the bit width. Okay, so actually, if you treat this as a 32-bit number, there are leading zeros. There are a lot of leading zeros, right? And precisely there are 28 of them. So built-in CLZ function gives you this value 28, and you subtract this 28 from 32 to get 4, which is nothing but your size, which is nothing but your bit width. Okay, so which is nothing but your number of bits also. So this is your number of bits, and this is essentially the minimum n that you want, and you do not want to use this n at all. Yeah. So what do you do now? You need to find the reflected index. Okay, so k reflected, we will try to find. Uh, this is our reflected index. So we want to reflect our index. So if this is our index k, we will call this index as a k reflected. Okay. Okay, so this k reflected will be nothing but, I hope you do realize, this will be 1 2 to the power of size z. So 1 left shift size z means 2 to the power of size, okay, uh, minus k. Okay, so you can see how this formula is derived. Mm, you just, this is, if this is the whole length, 2 to the power something, okay, if this is the whole length, you just reflect that. You just reflect that means you subtract this value from this. That's how you get the k reflected. So 2 to the power of sz minus k will be your reflected index. You can just take some examples and check. Yeah, and this is how you typically calculate your reflected values also. This is quite trivial. And yeah, once we have this reflected index, okay, we can pass this reflected index up our recursion. Okay, but if you see this reflected index, in case this reflected index is equal to this k, this means that you are in the middle element right now and you need to return 1. So this is your another base case, right? Do remember to do this at that. And once you get your reflected index, you can pass this reflected index into your next recursion. Okay, the next recursion, see, this reflected index remains same for the previous string also. So you just pass it up. You can just tell it like that. uh, Find k width, and you have n and reflected index. Okay, now if this reflected index gives you something out to be 1, so the thing is, if it gives you something 1, you can return 0, right? You can return 0, otherwise you can simply return 1. So you are inverting the bits, right? So basically when you are reflecting, you are inverting the bits. So when you want to pass it up your reflected value, so you also want to invert the bit because it was a 0 over here and it is getting a 1 over here. So you want to reflect this bit. So if that is 1, you return 0. That is, you pass 0 up. Okay, or while backtracking, mm, you just return 0 for the next recursion. Okay, so otherwise if it is 0, you just return 1. So that is all. That is all. If you try to run this code, I hope this will work just fine, and it was a simple code. Let's do some debugging. So we have this as character, right? So uh, do I need to convert all of these into characters, as the output must be a character, okay, not a string. Let's try to run and check. Yeah, we have it accepted. Let's try to run for all test cases and see if it works. Yeah, it does pretty well works for all the test cases. We have a decent runtime as well as memory complexity. And I hope you did understand the solution. If there was any doubt, you can definitely ask me in the comment section. So yeah, that's all. That was all from this video. I will meet you in the next video. Till then, thanks a lot.